All right, now we got work energy problems. Let's write down the work kinetic energy theorem, which says the work done is the change in kinetic energy. That's not a helpful form of it though. For work, I'm going to write force times distance. And for change in kinetic energy, I'll write 1/2 mv final squared minus 1/2 mv initial squared. So we end up getting F times D equals 1/2 mvf squared minus 1/2 mv initial squared. Meow. Okay. So A says the box is sliding at a speed of this much, comes to rest. And this is the distance. We have the mass. We want to know the work done. Not the force, but the work. So when we try this, we are sorely disappointed. Instead, we're going to use the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. That's going to be 1/2 times 2 times 25, because that's 5 squared, minus 1/2. I'm so sorry, I have it backwards. EK, so 1/2 mv final squared minus 1/2 mv initial squared, which is going to be 1/2 times 2 times 0 squared minus 1/2 times 2 times 5 squared. So we end up getting negative 25 joules of work. That's perfect because we're bringing it to rest over a distance of 4 meters, and negative work means slowing you down. So the force of friction that brings the box to rest, that will be calculated using the following. Now I can use this formula down here. So work is force times distance. And I have negative 25 joules equals the force times this distance of 4. So when we actually isolate the force, it ends up being negative 1.25 newtons. A small little caveat. When I say the word friction, don't get hung up on it. The fact is, when I'm asking you for the force, I'm asking you for whatever the force is that's doing the work. So you just use the numbers to solve for that missing force, and you kind of go back and realize, oh yeah, of course, the force that slows me down is the friction force. Here, a 2 kilogram block slides down a frictionless ramp from a height of 4 meters. Once it hits the ground, slides to rest. What's the friction force? So I want to be clear here, frictionless. And we're up here. And to be clear, this height is 4 meters. And then we have a rough surface here, which I draw like that. Rough, 8 meters. So the idea here is that if we were to do a bar graph, we have EG. And this is going to be part 1 of the problem. And then it becomes all dissipated at the end. So we have mgh equals 1/2. Oh my gosh, I'm so sorry. We have mgh becomes dissipated energy. So the dissipated energy as it slides to rest is going to be 4. I'm so sorry, it's going to be 2, which is the mass, times 10, which is g, times 4, which is h, and that ends up being 80 joules. Now this is ED, 80 joules dissipated. Now we are saying that this 80 joules is the work done by friction to bring the box to rest. That's the whole point. So we're going to say the work done is negative 80 joules to slow it. So we have negative 80 joules equals this applied friction force times the distance, which is 8. So we get negative 80 equals F times 8. And the force that we actually apply is negative 10 newtons. So that's the answer to that little part there. In the next video, we're going to take a look at the impulse momentum portion.